everybody. Today you're going to be looking at our reference page 11, which is in the folder for you to print out. So copy as we go along. We're going to do something of a crash course in right triangle trigonometry. Now, I would say about 99% of you have already had a little right triangle trigonometry. For example, you know Pythagorean theorem, and you may know the ratios for sine, cosine, and tangent. But let's just have a little crash course here in understanding right triangle trig, because before we can start looking at adding perpendicular vectors, we have to be able to do this, okay? Because this is a skill that is used when adding two perpendicular vectors together. All right, so basically what we're going to be doing is all mathematical, no physics here, just looking at a right triangle and how it works, okay? Now, as you guys know, a right triangle is a special triangle. It's not just any triangle. A right triangle, one angle inside the triangle is a right angle, 90 degrees. The side across from that is called the hypotenuse, and it is always the longest leg of the triangle. So if you are solving for the hypotenuse and you get a value that is less than either of these legs, you know you've done something wrong. So think about the answer that you get. If the answer that you get is really, really large compared to the legs, then stop and think. Did I take the square root in the Pythagorean theorem? Because people forget that all the time. I'm going to assume right now that everybody understands how to use the Pythagorean theorem. The hypotenuse squared is equal to the sum of a squared plus b squared, the other two legs, the short leg and the long leg. So we call them the hypotenuse, the short leg, the long leg. A and B. We square both, sum them, that equals c squared. If we want to solve for c, we take the square root of both sides. A lot of times, I'll see students, they'll square A, they'll square B, they'll add them together, and then they forget to take the square root. If you forget to take the square root, the value that you get for c is going to be way bigger than either of these. I mean a lot bigger. For example, you might have 8 and 9, and you get 64 and 81, you get 140 something, okay, 130 something. So when you get something like that, stop and think. That cannot be right, okay? Now, let's talk about the angles inside the triangle for a moment. All right, typically the angle across from the short side, side A, is called angle A. Now, in physics, we do not use the angle symbol that you used in geometry, which looks like this, okay? We don't use that. We actually use the Greek letter theta to represent an angular measure. So this is angle theta, and because it's this the angle across from side A, we call it theta sub A. This side has an angle across from it. We call it angle B. Using theta, we'd say theta sub B. All right? So, side A is across from angle A, side B is across from angle B. The hypotenuse is always across from the right angle. Now, Pythagoras realized that there are some relationships between the sides and the angles inside the triangle. In fact, he found that if you have two similar triangles, for example, if I drew a triangle similar to this one, like this, if we have two similar triangles, the angles inside are the same. And interestingly enough, if that's the case, if the angles inside are the same, even though the legs are not the same length, you would get the same ratios if you said A over C and A over C here. even though the numbers are different, their ratios would be the same. You might have 10 over 12 here. You might have 5 over 6 here, but the two ratios are the same number. Likewise, you would get the same ratio if you said B divided by C on either one. Or if you said A over B or B over A for each one, you would get the same decimal value if you divided those ratios. Now, Pythagoras realized that means that anytime you have a triangle, when you have a ratio of legs that has a particular value, it's always going to be across from or adjacent to a particular size angle. Now, there are three basic ratios. He happened to call them sine, cosine, and tangent. Now, this is just an acronym for what sine, cosine, and tangent are equivalent to. This is just a nice little acronym to remember. The sine of any angle is when you find the ratio of the opposite leg to the angle divided by the hypotenuse. The cosine of any angle inside the triangle is the adjacent leg to that angle divided by the hypotenuse. The tangent of any angle inside the triangle is the opposite leg to the angle divided by the adjacent leg to that same angle. These ratios have numerical values. And for any triangle with legs that have the same ratios, the angles will be the same. Now, back in the day, when I was in school, we had to learn how to look up the sine, the cosine, and the tangent on trig tables. It's a set of tables where you had every angle from 0 to 90 listed. Some trig tables go by half degrees, some go by whole degrees, but then they would list every possible sine, cosine, and tangent ratio for each angle. So, all you had to do to find the sine or cosine of an angle is know the angle and determine, if you know the hypotenuse, you could determine the opposite leg by finding the 4-digit decimal represented by the ratio in a trig table. So if you knew the angle and the hypotenuse, you could look up the sine of that angle, set this ratio equal to that decimal value, and solve for the unknown side. Likewise, if you know the two legs, you could look up the sine of the decimal and see what angle it goes with. That's what we call the inverse function when you do it backwards. Look up the angle instead of the ratio. All right, what we're going to do though is we're going to take a look at how these angles are related, because there are some very interesting relationships between them. So let me blow this up. Sorry. That's good. That's good. All right. So we're going to do this. We're going to draw some lines here to separate these. Okay. So now we're going to take a look at the sine, cosine, and tangent functions. What side is the adjacent and what side is the opposite depends on what angle you're looking at. For example, if I look at angle A, the side opposite angle A is side A. But if I'm looking at angle B, the side opposite angle B is not A, it's side B. So whatever angle you're looking at, you have to judge from that angle what is opposite and what is adjacent. Now, so let's take a look. The sine of an angle. In this case, we're going to use angle A as the angle that we're going to be focusing on. So if we wanted to find the sine of angle A, then we take a look at angle A. The side opposite is A, the hypotenuse is C, so we get A over C, which if you had numbers, you'd divide it and you'd get a decimal value. You could look that up on the trig tables and figure out what the angle is. Now, why don't you have to use trig tables today? You don't have to, because they're in here. That's why the calculator can do this stuff for you. It has the trig tables inside. So if you want to find the inverse, if you want to find an angle, you take the inverse sign of this decimal ratio. You just divide the two numbers and you get a decimal, and then you take the inverse sign and it looks it up on the trig table for you and tells you what angle has that particular ratio. Okay? Now, let's look at the cosine of angle A. If we look at the cosine, it's the adjacent over the hypotenuse. So the adjacent leg, the bounding leg, not the hypotenuse, but the bounding leg is B, and the hypotenuse is C. There goes the clock. The tangent of angle A would be the leg opposite divided by the leg adjacent. So if we go back up here and look, the leg opposite is A, adjacent is B, so that's going to be A over B. And you may be thinking, well, that's okay, so what? We're not done yet. Now let's focus on angle B right here. Now remember, opposite and adjacent depends on which angle you're looking at. So if we want to find the sine of angle B, then we come over here, we look at angle B, the opposite leg is side B, and the hypotenuse is C. For angle B, the sine of the angle is B over C, not A over C. The cosine of angle B. The cosine of angle B would be the adjacent leg, which is A divided by the hypotenuse. So for angle B, it's going to be A over C. Now, what do you notice? You notice that, interestingly enough, the sine of one angle is the same as the cosine of the other. Look at that. Isn't that interesting? Well, I think it's kind of cool. The sine of one angle is the same as the cosine of another. Now, let's talk about the tangent of angle B. Okay? If we look at the tangent of angle B, it's opposite over adjacent, so that would be B over A. So now look, the tangent of the angles in a right triangle that are not the right angles, the other two angles, their tangents are reciprocals. And that's kind of a neat relationship too. All right, we have one more. Let's take a look at angle C.
But Miss Pepitone, angle C is the 90-degree angle.
Well, it doesn't mean we can't look at it, so let's take a look. If we are going to look at the sine of angle C, the definition is the opposite divided by the hypotenuse. So here we have a problem. All right. Oh, look, the opposite leg is the hypotenuse. So what do we get for the sine of angle C? We get C over C, which is 1. This is why if you stick 90 degrees in your calculator and you hit sine, you get 1. Okay? Because it's hypotenuse divided by hypotenuse. All right, now let's look at the cosine of angle C. Cosine, remember, is adjacent over hypotenuse. So let's look. Here's the 90-degree angle. All right. Which is adjacent? And which is adjacent? You got A and B. Can you choose one over the other? Actually, no, you can't. They're both adjacent. And there's no way you can use both of them. And you can't pick one over the other. So basically what we have is 0 over the hypotenuse, which is why any number divided into 0 gives you 0. If you stick 90 degrees into the calculator and hit cosine, you're going to get 0. All right? Now, last one. Let's look at the tangent of angle C. All right? Tangent is defined as the opposite leg divided by the adjacent leg. So let's look. All right? Here is angle C. And the opposite is side C, the hypotenuse, and the adjacent leg, oh, well, there's that problem again. We cannot pick one or the other, and we can't use both. So when it comes to the tangent, we get opposite over nothing. We can't pick one or the other. And what happens when you take a number and divide it by 0? Oh, it's undefined. And if you try to take the tangent of a 90-degree angle in your calculator, what does it do? It gives you an error message. Okay? So these are the relationships between the various ratios that define sine, cosine, and tangent. Remember, they're just ratios. They're not some weird mathematical process. All right? Now tomorrow, if I can remember when I get to school, I'll get one of my old physics books out and I'll take a photo of some trig tables and post it in today's folder for you guys so you can see what they look like. They'll have these ratios in decimal form. They just actually take the two values and divide, because if the ratios for one triangle are the same as the ratios for a similar triangle, then no matter what the numbers are, you're going to get the same decimal. Whether you say 6 over 12, which gives you 0.5, or 5 over 10, which gives you 0.5, you know, that angle is going to be the same for both because they have the same sign decimal. They have the same ratio of legs. Okay? All right, now how are we going to be using this to help us with our vector addition skills? And I don't need that there, so I'm going to just get rid of it. All right, well, the one thing we have to do when we're using perpendicular vectors is we have to be able to determine the direction. And unfortunately, it's not like collinear vectors where you can say, oh, it's east or west or north or south or positive x hat, negative x hat, positive y hat, negative y hat. No. When you are looking at vector addition of two perpendicular vectors, the resultant is at some angle to the horizontal. And we always reference our direction from the horizontal. We'll talk more about that in the next little video on coordinate systems. But in order to do that, we have to find the angle next to the horizontal, the angle between the resultant and the horizontal. Now, how do we do that? Okay, we're going to use theta A as our example. Suppose that you want to find the value of theta A right here as the direction of your resultant. Maybe it's north of west or above the negative x-axis. What you want to do is you want to be able to find this using one of these functions. Well, now, if you've already used the Pythagorean theorem, you've probably got all three sides already. But there is a wiser choice on which one of these to use. Now, notice that two of them use the hypotenuse, which is fine. If you've already used the Pythagorean theorem to get the hypotenuse, it's no problem. You can do it. However, what if you did boo-boo finding the value of the hypotenuse? If that's the case, then if you try to use the hypotenuse with sine or cosine to get this angle, it's going to be wrong because your hypotenuse was incorrect. So the smart choice is to use the tangent function, because if you're given two perpendicular vectors, then side A and side B are given information. They're not wrong. So you should still get the correct value for the direction, even if you messed up on the Pythagorean theorem for the magnitude. Okay? How do we do this? All right? Well, basically, look at the math. Okay? For perpendicular vector addition, okay? Oops, I need to put it so you guys can see it. Sorry. To find theta, which is the direction of the resultant, here's what we're going to do. We're going to use the tangent function to find the direction for the resultant. If you remember, that is the opposite leg divided by the adjacent leg. Okay? Now, we want to solve for the angle. We're going to be given the two perpendicular vectors that we're adding together. We know those. We want this. So how do we isolate it? What do we do about this? Well, to get rid of a tangent function, you do the inverse tangent. And if you take the inverse tangent of both sides, these two cancel and leave you theta, which is exactly what you want. You want to isolate the angle. And over here on this side, you're left with the inverse tangent of the ratio opposite over adjacent. Or, in our case, because we always reference the direction from the horizontal axis, whatever the closest horizontal axis is, then we can always say it's the inverse tangent of the y-plane vector over the x-plane vector. Okay? Whichever one is in the y-plane divided by whichever one is in the x-plane. Okay? I'll show you more about that later. But basically, this is how we're going to find the angle theta in our problems for perpendicular vector addition. Okay? Thank you for listening. Talk to you later.